square root of k minus 1 that appears. I didn't really motivate it. I motivated it through the universal cover, but it really comes up when you study finite connected graphs, and it comes up via an inequality. And so I'm still in chapter 2 on expanders, and that's section 2.3. It's the Alain-Bopana inequality. And it says the following, that if you take a sequence of finite connected k-regular graphs with increasing size, so namely that the number of vertices goes to infinity when I goes to infinity, then the lim inf as I goes to infinity of the first non-trivial eigenvalue of the graph xi is at least 2 root k minus 1. So this means that the first eigenvalue will be larger than 2 root k minus 1 minus epsilon, right? If you discard the finitely many graphs in your sequence. And this means that asymptotically the spectral gap of a k-regular graph, of the family of k-regular graphs, the spectral gap is at most k minus 2 root k minus 1. And you see, this condition is responsible for the definition of Ramanujan graphs. So Ramanujan means that all the eigenvalues, especially lambda 1, are at most 2 root of k minus 1. So what this means is that families of Ramanujan graphs if they exist, and okay, we know since this morning that they do exist, but this is highly non-trivial. So if they exist, they provide the best possible expanders from the spectral point of view. Namely, families of graphs for which the spectral gap will be the biggest possible. Okay, and now, well, let me discuss some tools used in the construction of of Ramanujan graphs. And so this will be now. Oh yeah, by the way, questions so far about Alain-Bopana?
Will you sketch the proof?
Of Alain-Bopana? Yes. Even something stronger. That's where I'm heading to, actually. So you are anticipating me. So let me discuss the trace formula on finite connected graphs. Okay, we know what a path in a graph means, so it's a sequence of adjacent vertices, but there are paths which are better than the other. And these are the so-called paths without backtracking. So, to give you an intuitive idea, suppose that you want to go from Brussels to Ghent by train. You may board a train that takes you to Ostend, and then you go back to Ghent. This is called backtracking. So, definition. A graph, let's say x naught, from between two vertices x and y, so x naught, x1 up to xn, which is equal y, and by path I mean the path of pairwise adjacent vertices. Is without backtracking.
Or you mean the path?
Oh, path. Oh, yeah, thank you. Thank you. At least one person is following. Path is without backtracking. If xi plus 1 is not equal to xi minus 1, and this should be for every I between 1 and, I guess, and minus 1. So you never retrace your steps. For instance, an example, suppose you have a circuit in your graph, and suppose you circle many times. This is without backtracking, right? So it's not the same thing as an injective path. These are two different things. And now, let me introduce a family of matrices that count paths without backtrackings between vertices. So, for R, any non-negative integer, I define a matrix A sub R, again indexed by pairs of vertices, and it could be symmetric as well. And AR sub xy is, by definition, the number of paths of length R without backtracking between x and y. And for instance, A sub 1 is just the adjacency matrix. A sub 0 would be the identity matrix. And there is an easy lemma, but it's both easy and crucial. What's happening when you square the adjacency matrix? Well, you get A2. Oh yeah, sorry. From now on, X is a finite connected irregular graph. So when you square A1, you get A2 plus K times the identity. Indeed, proof by hand waving. You square A1, so this means you consider paths of length 2, but all of them. So you have paths that take you at distance 2. So these ones do not have backtracking. And then you will take one step and then one step back. And because the graph is k-regular, you have k ways of doing that. And this gives you k times the identity. End of proof. Second. A1 times AR. Oh, okay, sorry. For this is for R at least 2. A1 times AR is equal to the AR times A1, and it is AR plus 1 plus K minus 1 times AR minus 1. Okay, maybe let me give you the hand waving proofs in the same way. Let's say for A1 AR. So AR takes you without backtracking to distance R. Well, and then you take one more step. So either you don't backtrack, and it gives a path without backtracking of length R plus 1, or it does backtrack, but because R at least 2, you have k minus 1 ways of doing that instead of k. And this gives you the k1 times AR minus 1. And those relations are sometimes called the Hackett relation. And using those relations, we get the generating function of this set of matrices of the AR. So generating function by definition is the sum of all possible r of a sub r times t to the r. We are not talking about generating functions. So this is a formal series. We don't talk about convergence. And this is equal to 1 minus t squared divided by 1 minus a times t plus k minus 1 times t squared. And this will be formula 1. What's the meaning of that? This means that if you take this series and multiply it by the denominator of the fraction, you get 1 minus t squared times the identity. That's the meaning to give to this formula. This formula is very interesting, except for one thing, which is the one, we would like to have 1 in the numerator and not 1 minus t squared. And to eliminate the 1 minus t squared in the numerator, we introduce a new family of matrices, T sub m, and again m is a non-negative integer. T sub m, by definition, is the sum over all r's between 0 and m over 2 of a sub m minus 2r. Okay, so new set of matrices. But the point is that using that, the generating function of the Pm's is, I do need space.
Is that even like
But say it again?
The natural number has to be even? No.
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 No. So it makes sense, even for odd numbers. No, it's really for every n. And okay, so the generating function is, well, again, sum for m going to 0, from 0 to infinity, tm. And in this time, it's a purely formal computation that it's 1 minus 80 plus k minus 1 t squared. And I think that this will be formula 2. Okay. And to go further, we must introduce a family of special functions, but classical ones, which are the Chebyshev polynomials of the second kind. But let me remind what this means. Chebyshev polynomials of the second kind, second kind. They are defined by um of cosine of theta is sine of m plus 1 theta divided by sine theta. It's a classical thing that if you expand the numerator using high school trigonometry, you find that this function is really a polynomial in the cosine function. Like for instance, well, okay, u0 is sine theta divided by sine theta, so it's 1. But u1, for instance, is sine of 2 theta, and so that's twice sine theta cosine theta. So you get, okay, let me, u0 of x is 1, u1 of x is x, and you see that the degree of um will be n.
It's 2x.
2x, thank you. 2x. And the point, and still again using the addition formula for the sine function, you see that there is a recursion formula, which is um plus 1 of x is 2x times um of x minus m minus 1 of x. And from this recursion formula, you get the generating function of the ums. And it goes as follows. Sum for m equals to from 0 to infinity of um of x t to the n. It's 1 over 1 minus 2xt plus t squared. And that's formula 3. And of course, you notice that 2 and 3 are somewhat similar. And we are going to make them even more similar by performing a clever change of variables. And so for the polynomials, okay, so k minus 1 to the m over 2 times un of x divided by 2 times square root of k minus 1 by if you perform this change of variable in formula 3, sorry, you get that the sum from n from 0 to infinity of k minus 1 to the m over 2 un of x over 2 root k minus 1 times t to the m. So this means the generating function of this new family of polynomials, this is exactly 1 over 1 minus xt plus k minus 1 times t squared. And so this means that this time the structure is exactly the same as in formula 2. And this allows us to deduce that t to the m is equal to k minus 1 m over 2 times so the Chebyshev polynomial applied to the adjacency matrix divided by 2 root k minus 1. So this means that basically this says that those matrices Tm are computable by classical polynomials in terms of the adjacency matrix. And now, okay, the chapter is called the trace formula. So what we are going to do now is to compute the trace of Tm in two ways. Because compute the trace of Tm, and because on let's say the vector space C to the V, so this means functions on vertices with complex values. And in this space we have two bases. We have the canonical basis, and we have a basis of eigenfunctions or eigenvectors of the adjacency matrix. In the basis of eigenvectors of A, we get the so-called spectral side, which says that the trace of Tm is k minus 1 to the m over 2. So here we have a polynomial in a diagonal matrix, but it's still a diagonal matrix. And so here we get the sum of over which variable is over j, from j to 0 to n minus 1, and of um of lambda j divided by 2 with the root of k minus 1. Okay. So that's just computing the trace of a diagonal matrix. while in the canonical basis, of C to the V. So that was the basis in which I defined my matrices A sub R. And so remember that, okay, Tm was a sum of Am minus 2R. So we get that the trace of Tm is the sum over all vertices X, the sum for R between 0 and M over 2 of Am minus 2R XX. But remember, this is a combinatorial interpretation. This is the number of paths of length 2M minus R without backtracking from X to X.
Minus 2R.
So say that again.
Minus 2R?
Yeah, thank you. This one is correct, and this one is false. Thank you. And M minus 2R. And the trace formula is just that this spectral sum is equal to this combinatorial sum. That's the trace formula. So if you look at the spectral side, it's by no means obvious that this is an integer. It's by no means obvious that this is non-positive. And as an application, let me show you what the mere positivity of this stuff is doing. Consequence of positivity, or maybe I should say non-negativity, of the spectral sum. And right now, I mean, for the next two results, due to a famous French graph theorist whose name is Jean-Pierre Serre. Something he did in 1997. So he was 71 when he did it. So I have high expectations for my own future. So okay. So first, well, he provided an analytical result that I'm not that I will accept as a black box. It's a result really on the Chebyshev polynomials. It says the following theorem. Take L will be a real number, at least 2, and epsilon is some positive number. And what that's true is that there exists a constant C, only depending on L and epsilon, such that for every probability measure mu on the interval minus L, then you assume that this probability measure gives positive integral with that, against all Chebyshev polynomials. Well, the explicit assumption is that when you integrate over the domain, so from minus L to L, un of x over 2 d mu of x, you assume that this is non-negative for every n. That's the assumption. Then, when you take this measure and evaluate the length, the measure of the interval 2 minus epsilon L, it will be larger than this constant C. Okay, so that's a basically analytical result, but now let me give you immediately the consequence in graph theory. So the corollary is the following, that again, fix k, that k will be the regularity of the graph, and epsilon, and so there exists a constant C only depending on epsilon and k, such that for every finite connected k-regular graph x on n vertices, the number of eigenvalues of x which are larger than 2 minus epsilon root times root of k minus 1, this number is at least c to the n, c times n, sorry. And n is the number of vertices. So this means that as soon as c times n is larger than 2, you know that lambda 1, well, lambda 0, which is k, is always there. But as soon as it's larger than 2, you know that lambda 1 is larger than 2 minus epsilon root of k minus 1. And you see that this gives much more. It says something about other eigenvalues. It tells you that there is a positive proportion of eigenvalue which is larger than 2 minus epsilon times root of k minus 1. And the proof, assuming the theorem, is the following. You take for L k divided by root of k minus 1, which is larger than 2. Mu is 1 over n sum for I to 0, from 0 to n minus 1 of the delta function at lambda I divided by root of k minus 1. So this means you take the eigenvalues, normalize them, and take the Dirac masses of those eigenvalues. So it's a probability measure with finite support. And you know that by the trace formula, and again, just assuming that the spectral side is non-negative, we get that the assumption is satisfied, namely the integral from minus L to L of um x over 2 d mu of x is positive, non-negative for every n. And hence, by hence the conclusion, if you take mu of the interval 2 minus epsilon L, and what is this? This is exactly the this is 1 over n times the number of eigenvalues, which are eigenvalues in the interval 2 minus epsilon root k minus 1 to k, that number will be larger than C. So that's the proof of the corollary from the theorem. Yes?
No, just trying to pass the theorem. So you're taking, so you're considering all probability measures that satisfy this inequality with the.
Yes.
Okay, that the conclusion is that the measure of the interval is at least C.
Yeah.
Okay, if for whatever reason, what happens if epsilon is too big? I mean, we wouldn't take epsilon big enough, but I mean.
No, epsilon is supposed to be small, smaller than 2.
Yeah, fair enough.
Yes. Ah, okay.
So, how explicit is C?
Pardon me?
How explicit is this C? If I give you k equal to 13,
Um,
1000,
good question. I have to go back to the proof. Sorry. And I'm.
Could you step aside a bit?
Sure. No, it's not. The proof is by contradiction, so it's not explicit. Mhm.
Sorry, can you explain again the mu?
The mu?
Yes.
Okay, so first you normalize the eigenvalues of the adjacency matrix by dividing by okay, that number. And then delta is the Dirac mass. So, so this means that if you have a Borel subset, the probability will be 1 if this number is in your Borel subset and 0 otherwise. And then you take the average. It still makes it, well, of course it makes it a probability measure.
I have a question about the trace formula. You know that the sum of the integrals is bigger than 0, but not necessarily each integral, right?
No, I know it for every n.
Why does it follow? Do you know it for the n?
So I hope I wrote it correctly because I just erased. But okay. The right hand side of the spectral side of the trace formula says that is this one. Yes. And what I'm using is that this is non-negative for every n.
So why do you get that the integral is, sorry, but let me stop that one. Well, why do you get that the integral for each n is bigger than 0? Can it be that some of them are positive and some are negative in a way that...
No, because this is not positive because it is equal to something that we obtain by counting, which is therefore a non-negative number.
Yes, but then as a function, like I do not understand why you get something pointwise per n. Maybe
Or pointwise?
There's some
It's
reason here.
It's already the integral with
It's an integral
Ah,
against a measure.
Oh yeah, sorry, it's an integral with respect to the finitely supported measure.
So,
Yeah, it's a question of measure theory. Yeah, okay. Okay, so many times, 7 or 8 minutes, something like that?
Yeah, 8 minutes.
Okay, so let me start the description of the graphs of Lubotzky-Phillips-Sarnak. Okay, so we're going to use the Hamilton quaternion algebra. And take a unital commutative, oh sorry, maybe A is probably bad. R, a unital commutative ring. And actually, I will use it for the integers for the finite field with Q elements. And H of R is the standard quaternion algebra, so it's R plus, and you introduce three symbols R, I, J, K. And you have the relation that I square is J square is K square is minus 1. And then Ij equals K, and it's minus Ji plus cyclic permutations. Do I miss something?
It's an associative algebra.
Yes. Okay.
No,
You should be whipped for that remark.
that's how you lose your job.
I thought you were about to answer, your time is over. Okay, so that's a standard. And oh yeah, so Q, if Q or maybe alpha is A0 plus A1I plus A2J plus A3K, and where the AI are in the ring. And we have something that's called the norm in algebra. So the norm of alpha, n of alpha, is A0 square plus A1 square plus A2 square plus A3 square. And it's, as we know, the norm is multiplicative. And so, of course, it's the norm for algebraists. Those people do not know about square roots for good reasons. So, so we don't take the square root. That would be a sin. Okay, and yeah, and now take P prime. And there is a classical theorem by Jacobi that the number of integral solutions of the equation A0 squared plus A1 squared plus A2 squared plus A3 squared equals P. So the number of those, you take all integral solutions, in positive or negative or zero integers. And the number of those solutions is 8 times P plus 1. So Jacobi proved that around 1840. And of course, if we reinterpret this in terms of integral quaternions, so in H of Z, this says that the number of integral quaternions with norm P is 8 times P plus 1. And there is a definite advantage to adopt the quaternion view, the quaternionic point of view, because, for instance, we know that the group of units, the group of invertible quaternions in H of Z is a very small group. It's a group of order 8, plus or minus 1, plus or minus I, plus or minus J, and plus or minus K. And this group is acting on the set of solutions, of the set of quaternions, acting, let's say, by left multiplication. And so we see that the factor 8 really corresponds to the order of the group. Something that's probably, without the quaternionic point of view, it's probably less intuitive. And and now, okay. Assume for simplicity that P is congruent to 1, not 4. Reducing mod 4. So remember that the squares mod 4 are exactly 0 and 1. So if we take this equation and reduce what was mod 4, we get that the sum of 4 squares must be 1, modulo 4. And this means that exactly one of the AIs is odd, and all the other ones must be even. Okay? We see in the equation n alpha equals P that exactly one AI is odd, the other ones are even, and using the action of the units, we may assume that it's A0, which is odd. So and so we get the set SP. So that will be the set of integral quaternions of norm P, and such that A0 odd and the other ones even means that when you reduce this quaternion mod 2, you get exactly 1. So alpha is congruent to 1 modulo 2. So that's the definition of the set SP. And we see, because of Jacobi, that the cardinality of SP is exactly P plus 1. Moreover, you have the conjugate. I forgot to say that. Each quaternion has the conjugate, when you replace I by minus I, J by minus J, K by minus K. And you may write actually SP as alpha 1 bar, alpha 2 bar, like 2 alpha p plus 1 over 2, and its conjugate, alpha p plus 2, p plus 1 over 2, quaternionic conjugate.
I think you need to ask some. You will get 2 times p plus 1. I think
But you
you
divide
want
it by 2.
a0 to be positive. To assume a0 is odd and positive. To kill the extra freedom.
But dividing by 2, mod 2 gives you, I think, that. Instead of mod 4.
Pardon me?
The mod 2 you did gives that, I think, no? Instead of mod 4, dividing by 2.
There is a unique unit which will make a0 odd and positive.
Yeah.
Okay.
You want to select one orbit representative.
Yes, that's correct. I want to select one orbit representative, so odd and positive. Okay. Thank you. Yeah, well, I think that's all for today.
So we have time for any question that does not concern the associativity.
Exactly.
What about octonions?
So it's important that P is a prime number, so we don't have one that is the same as its conjugate.
Yeah, that's correct. Yeah.
Or at least not square.
Just so I understand correctly, you can prove Alain-Bopana using this corollary, right?
That's something even stronger, because here,
Yeah.
I mean, as I said, it says something not only about lambda 1,
Yeah.
but also about the
Okay.
other eigenvalues. Yeah, it's strictly stronger than Alain-Bopana.
Yes.
They are best from the spectral point of view, but we saw with the Cherev-Riemann inequalities. So what about the isoperimetric point of view? Like, are there other graphs than that?
That's a very interesting question, and I'm not sure of the answer. I think that there is a paper by the late Bob Brooks who investigates precisely how bad or good the Cherev inequality it can be. But yeah, that's all I can say on the top of my head.
So you cooked up this generating function for either A or
Yeah.
T, and then for this guy you could get a nice formula. So if I remember correctly, there's also a zeta function that counts whose coefficients of the Dirichlet series count the closed paths in a graph.
Yes.
Is there something similar for this zeta function? Is there also some kind of
Yeah. The point is that the graph is Ramanujan if and only if the zeta function satisfies the Riemann hypothesis. So, for zeta functions, so all the non-trivial zeros are where you think they should be.
Thanks.
Just a weird question, I guess. So in this theorem by Serre, you have this assumption that mu is a probability measure that assigns positive measure to any.
Chebyshев polynomial.
Yeah, exactly. So this trace formula gives you one such measure, right? One example. Of
Yeah.
such a measure. Can you say anything about other measures? Like how many measures are there?
Okay. I think that if you are in measure theory, this is a very interesting question, and the honest answer is I don't know. Yeah, but no, from the point of view of measure theory, it's a fairly natural question. But I don't know, and I think I never saw anything about it.
But doesn't the proof use some kind of density argument?
So,
I seem to recall that the proof of that fact uses some kind of density arguments in the spaceable measures. And
I don't think so. Again, let me check. No, there is a compactness argument that gives you precisely the lower bound. I mean the fact that C is positive, but no. There's no density argument. But there is a compactness argument, as expected, so to speak, because once you talk about probability measures.
Okay, is there any more question? So Alain, I wanted to ask you, you announced 2 results by the famous French graph theorist.
Oh yeah, this one and the corollary.
Okay.
Yeah,
Okay, so I suggest we thank the speaker again.